So then again, we are trying to find we're trying to transform a distributed load, in this particular case linearly distributed load, to a point load, right? A common representation of the linear distributed is a key, right? I'm just going over this real quick. It's a key, right? Key is key, but usually we end up this using was the symbol for uniform distributed loads to describe linear distributed load, right? Because what we do is that we use W, or a value up here, meaning it's describing this point here from up to down to describe it, right? But then there's some slope and something. This is just something. So our main aim here is to transform this distributed load, linearly distributed load, to a point load. Then again, for this one too, what happens is that we put the point load that we transform it to just at the center. But then this is not as we're having for the uniform distributed as a triangle, sorry, some sort of rectangle. We put it at the center. If this is about 6, right, the whole length is 6, we end up putting it at about when we transform it, we end up putting it at about here, which is, let's say, 3m, right? This is different. Here we're having a triangle, right? So what we do is that in order to do that, we have to find the centroid of a triangle, right? And the center of a triangle, there's actually something being done to find the position of the centroid, right? If we have it to be this way, right? If we're to be this way, let's say rectangle, it's just at the center, right? Because this side here, the thickness, let me just go over this side, the thickness is the same as about the area here, right? But in order to get a centroid for this particular triangle that we are having here, what we say is that there's one side where we have to move more in to the area of the shape in order to find the centroid, and there's another side where we move less than the other side to get a centroid. It's already been found, but I'm just saying this so when we understand it, you don't have to memorize it, you just get the concept and you'll be fine. This is what's happening, right? So we want to be a rectangle, because the areas here, the area here are the same. We just say just at the center, right? But here's the case where the area is not the same, right? So if you try moving from here, there's a way you have to get to the center. If you try moving from here, there's a way you have to get the center to the center, right? But in this case, we are assuming that short. That's what we do. We assume that the coordinate system start here, right? And then in order to get to the center, you see, because this one here, if you, let's say for instance, I do something of this sort about here, right? You see that the area here is smaller somehow than the area here. We are just assuming, right? So meaning that if you want to move to the center from this position, you have to go more, right, of the length. So the actual thing there is about 213L. So if from here to here I have to move about 213L to get to the center, right? But if I'm moving from the right hand side, because this side we are assuming is a big area, a bigger area than the other, right? So this one is about 213L. But if I'm moving from this side to the center, I don't go much as the other, so it's about 113L. Yes, yeah, so that's it. So that's how we place the uniform distributed load for this particular one, right? So now we're going to put it at this position on the diagram, the first diagram of the entire beam, to see where to be. So this is where to be. We know the full length of the beam, so to be about here. If we are trying to put the point load here, we know that from here to here will be what? Will be 2 on 3, right? As we've seen, 2 on 3, right? L. And then from here to here will be 1 on 3L. Then again, this whole thing is based on the full length of the beam. If we're to be given a value here, right, about 6, we can define what from here to here the distance, right? So just 1 on 3, that will be about 2. That will be about 2 units, and then from here to here, that will be on 2 on 3 by 6. But here we are just giving L, so we work by that, and then that's what we get. So this is what the point load will be. And then what's happening is that we are changing a distributed load to a linear distributed load to a point load. So the magnitude here, that's how to be. Now let's write the magnitude. Now we know the distance, we are trying to write the magnitude. If we're to be this one, right, what we did was that we know from this one here is about W, and then from here to here it's about the length, right? So if it were to be this one, if we're trying to make it to a point load, you can check the other video. What we just do, the other discussion, what we just do is that we multiply the W here by the entire length that is acting on. If it were to be, let's see, about 6, if we're acting on the whole length, let's see about L, just 2L here, and this gives us our point load about here. That's the WL, right? But here the area is different. So what do we do about the area? There's a triangle. So what's the area? That's half times base times height, right? So it's acting on the entire beam. So when you look at this particular uniform distributed load, here is a triangle, linearly distributed. Sorry, it's a triangle, right? So in order to get the point load, the magnitude of it will be half times base. It's acting on this whole length, right? And what's the height? The height is this, right? So this is basically a linear distributed that we are using a uniform distributed symbol W to determine the what do you call it, the height here. So this way, right? Let me put this somewhere properly. So this right here will be over here. If you try to transform this, yeah, so that's how it will be. If we decide to transform this into a point load, right, so we end up getting this right here. So the origin is still the same. We are converting this to this, so the origin is still the same here. So from here to here is 2 and 3L, from here to here 1 and 3L, right? Now I move to the next one. Just the same thing, but just that it's not at the origin, right? It could be anywhere. So this is how we go about this. It's just the same thing. We put it at the center. How do we get the center? We know that from here, it starts from somewhere, ends at somewhere, and that magnitude, which is from here to here, is 3, right? So the middle of 3 is about 1.5, right? So we know that, but the coordinate system starts from here, so we move about 1 before we get to the center of here. But we know that the center here is about 1. If we start from here, it's about 1.5, and here is 1. So in the end, we're not moving right. We're not moving from the origin 2.5 to get to where it is, right? So this is how it would be. If we put the if we put the force here, the point load that we are transforming to here, the distance will be, so yeah, now this one. I'm talking about this now. I'm talking about the other one. So the point load from about here to here, which is where the coordinate system starts, will be what we've established. That will be this 1.5 plus this one here, which will be 2.5 meters, right? Now the next thing to do is that we need the magnitude of the force, and what would that be? We say that together we do half times base times height, right? So that would be half, right? Let's see, half. What's the base? The base is just saying where the base of the triangle, right? The triangle formed by the distributed load, right? There's a triangle here, and it's acting on just these 3, right? So half times base, which is 3 times the height. The height is this 30, right? So this one, you see, because you have values, we end up getting an actual value. So let's see, half times 3 times 30. Let's see what we are getting there. There's also another case. I'll add it to this one, but if you want, you can skip that one. There's also another case that when we are trying to section. So let's find this one first. Times 3 times 30, right? So that gives us, yeah, that gives us 45. 45, right? So that gives us 45, right? 45 for the point to the magnitude of it. That will be 45 kilonewtons. No more kilonewtons per meter. So kilonewtons, right? So there's the magnitude, and there's the where it acts, right, respect to the origin, where we are seeing that the origin starts about here, right, and then moves this side, right? Yeah, so that's it. All right. Then again, but I'm going to discuss something different, very similar but different. There are some cases, especially in cases where we try to section, right? When we are sectioning now to see what's happening in the beam or find deflection or whatever, when you're trying to find the equation of the elastic curve, right? There's a way. If you are okay with what we just did, you can just keep the side, right? I'm just adding it because it's used this particular example. This one right here, let's see. This one, yeah, this one. So I'll copy it and then continue with that one. Where we have to section and then see what's happening. I've already discussed how we do the sectioning and how to even find the maximum section that you can do within the diagram, right? So to do that, this is what we do. I'm just going like over this like we've done it, but you can check the Castellano discussion. For that one, I even talked about the section and everything, right? So to check the number of section I have 1 and 2. So the section will be about here, just one section. So if I'm doing the free body diagram of this free body diagram, if I'm doing a free body diagram here, right? If I'm doing a free body diagram here, this will happen. I'll end up getting a free body diagram of this sort. Let's see. It's just one section that can be done, so just section 1, right? So it will be this way because coordinate system is starting. I'm sectioning 2, right? So it's about here, this, and now this, right? Then bring it close to be similar to one section. So I'm sectioning about here. So it starts from here, starts from here and goes about here, right? And then I have this, right? This about O, and I have my shear force here, and my moment here, right? And then at this point here, at the fixed end, I'll have a reaction there about this, right? Which is mostly term AY. Here we're just seeing how we do it, right? So we have about everything. The coordinate system is the same thing, right? So let me just do this, right? So I have everything. I have the shear, I have the moment. The next thing I have to do is to be able to represent the same, what's the name, beam, the same distributed load, linear distributed load here in the form of a point load, right? So what happens is that if we section, we actually know that this one here is actually for the end. So if we section, we end up getting something of this sort. A linear distributed load here, right? This way, right? But then we don't know the exact W that is here. So let's say W naught. Let me make it W1 because it's a free body diagram 1. We don't know the actual W that is there. So if you are even trying to do some force balance, you won't be able to find exactly the value for the W, right? But there's a way to go about it. This one says is that you see that because we have a triangle, if you have a triangle this way, another triangle on the inside. So basically, this one is for this big triangle here. Let me say a different color, right? For this one here, and then this small triangle. It's for the one down there. Let's see. This small one here is for this very one. You actually get to see that this WI is actually a part of the W, right? So if I'm trying to change the W there to a point load, let's see the same free body diagram. This how to be free body diagram 1 to be this sort. Let's see. So this and then this. You have this, right? O V this way, moment, right? And I have my AY here. This AY, right? The coordinate system is the same. The only thing needed now is how to transform this uniform distributed load here to a point load and to be able to resolve the forces, right? this one here. This is how it's done. You get to see that this W, as we're saying, this WI here is actually a part of this 4W here, right? So by the way, this one here, the whole length is X, right? This whole length here is X, the same thing. Then we know that if I'm trying to transform this to a point load, it will be at the center, right? So from here to here, right, is about X on 2, right? And then what I need to find here is the W here. The W there, right? This is what's happening. I'm placing the W there. The W there is actually a portion of the whole thing, right? So let's see, we know it's still a triangle, so make 10 to the force half times base, which is X, times height, right? The height here, which we are saying the W, this one right here, we are saying it's a portion of this, right? So if it's a portion, first of all, let's write it out. This W here is a portion of the W. The W naught here, WI. Let's make this not. This WI. This WI is a portion of the W. So we can write the W, right? It won't help us to get a portion. So let's see. This is half times base, right? So the height is what we need. And we're seeing this particular height here. Like when we look at this particular triangle here, right? Look at this one here is this, and then this big triangle here is this one, right? So as I said, this height here is a portion of the bigger one. This one right here is a portion of this. You can go over the geometry later, but now to turn this one to a point load, we need half times base times height. We found half, we found base, right? And the height is W. Whereas since this W1 is a portion of W, right? So W, we'll make it a portion, right? We need a fraction. And what's the fraction? The fraction is saying you're using the length. This whole length here is W, right? And this whole length here, this whole length here is L, and this whole length here is X. So the fraction that we'll get will actually be X on L, right? So this right here is the force acting at this side, just the force. So if it happens that we want to do a moment balance about the point O, this is how it will be. Let's go over this. So if we want to do sum of the moment about O, means this is how it will be. We get this direction is this way. So we get M, right? The next force that we encounter is just this. So M, which is in the same direction as the M. So this is the actual force, half times the base. The base is X, right? And then the height is what? W0, right? Oh, there's a mistake with this one. We'll talk about this one later. Base, and then the height. The height we are saying is a portion of the big one, which we've written here. So that's times X on L. So let's put this together. We end up getting W naught X on L, right? So this is the force that we've written out. But what is the distance? Then again, when you look at this, we said it's a triangle. To get the center of the triangle, this one is situated at the center. And then we established that if you are moving from if you have a triangle, you're moving from this side, you have to go in more, right? So 2 on 3 of the length, right? If you're moving from this side, it's 1 on 3 of the length, right? But here's the case, you're moving from the left hand side, because that's where the origin of our coordinate system is, right? So that's how to be. So we have M, we are doing moment balance, we have M, we have the force, which is half times base times the height, which is this. Now we need a distance, right, to make it a moment, right? And we are picking it from this side, right? Since the triangle, we are moving in more here. As well, 2 on 3x, right here. This is the whole thing of it, the whole length of this side, right? So end up getting. Let me make this yellow, which is 2 on 3x, right? And all this is equal to 0. So this is the equation, the moment equation for this particular one, for this particular free body diagram when we do it, right? So expand this. Let's see what we get. This goes out. So we have if you are moving this, it becomes a minus, right? We have a W, this is out, W naught, and then you have what? X. And note this W naught, as we were looking at up there in the diagram, it's not the same as the WI, right? But we know the W naught, that's why we use that one. That's the most cases that we're able to know the WI. So we have W out, X out squared, actually S cube. This is cube. So X's are 1, 2, 3, right? And then what do we have? We have 3L, right? So we have everything out. So 2, 2 gone. W naught, X is 1, 2, 3. Oh, let's go with this to make sure we are doing the right thing. Okay, let's see. Okay, so that's how it should be. Right, to get what we've written here, we are going over this one more time. We're going over this one more time to see if we have the same thing. Right, so first of all, we are moving it, we have a negative, right? And then we can cancel this 2 out, right? So on the top side, we have W naught, and the x's are our 1, 2, and 3. That's not O. X3, and then down what do we have? We have L, and then we have 3. So all on 3L. 3L. Yeah, so that's it. I was using this example to show that, like, when we are actually doing the sectioning, this is how we get the moment and the distance and everything. Yes, so that's it. All right.